Hello. This is going to be an interactive session. Hopefully you received the instruction to download the required software and the necessary data set, which is downloadable from this link. I know few of you have done it. If you haven't, you can just follow me on the screen. Just a little background. This workshop is based on a competition data set back in August 2018. There was a competition in Pennsylvania. It was Aquaphotomics data set, and 4 different solutes in water: acetic acid, potassium chloride, lactose, and sodium chloride at different concentration, measured under different perturbation, different temperatures, were presented as data sets. And the aim of competition was to be able to identify unknowns, the species of the solute, as well as the concentration of those in the near-infrared spectra that was presented for the competition. The concentration range was from 1 to 100 millimolar. Some of them are very low level, so below detection limit. So I'm going to present you the winner solution. One of the interesting result that we had based on this work, that we could identify solutes that were below detection limit. So I have some theory what is possible, but more theory tomorrow. So this will be more practical, so you have a feel for how to deal with the data and how you can pre-process in a different way, more along the line of what you just mentioned, EMSC sort of pre-treatment rather than spectral subtraction, which was what Dujan just mentioned. So I'm trying to avoid that problem of standardizing the spectra and subtracting them, which can not be always ideal because you can't control it perfectly. And the solution we are presenting is to look at orthogonalization, removing subsets of subspace of data that are orthogonal to what you're interested in, and therefore not worry about standardizing or controlling your experimental design. So data set available from this link, and the software I'm going to use is PLS Toolbox or Solo, which is the standalone version. Have you heard of this software before, or anybody's using? It's a very good software. So I think the best standalone software that I know of. Of course, it can be integrated in MATLAB, so you can program it. And that's what we did, because you need to do a lot of automation. So you need that automation part of it, programmability of it as well. But I will show you the standalone version and how you can analyze Aquaphotomics data. And nice thing about it is very good visualization and color coding features, which is normally missing in the publication that I've seen. You don't see the data, and you may miss the point if you don't visualize it. So hopefully I can make it interesting by showing you how you can bring out features out of the spectra that are otherwise invisible. So this is the workshop data set. You can drag and drop it into the workspace.
So this Solo is a program that you install?
Yes. There's a link on the abstract that I've submitted, and you have a 30-day free subscription to install and play with it, and after that you have to pay. But compared to many other softwares, price-wise, it's even more reasonable priced.
What is the range of the price? What do you want? Is it
Oh,
thousands, hundreds?
I think it's out of the remit of this discussion. But because I'm not representing them really, I think it's a useful software to deal with this type of data. So, but you can use R, you can use Python. All of these have equivalents in those other programming languages. So, is that clear enough? So, let me introduce you to the data set. CRX is calibration data, raw, X spectra, calibration spectra that are raw. Interesting thing about this method is you work on the raw data, no derivatization. Derivatization can cause problems. You lose information. You need to interpolate, you need to smooth, you need to have some assumption about the degree of smoothness. So the minimum pre-treatment, we just want to identify directions in the data set that are interference, and we want to remove them. And ideally, those directions are independent of your signal directions. And that's not always the case. Sometimes these two are correlated and collinear. So you can't always be. But for this data set, you will see it will work perfectly. And this one is Y. So the concentration data are for calibration are in CRY. T is test. So we can test the data set if you have time. I'll show you how we can predict the test set. Again, X for spectra, Y for concentration. For the competition, there is also a validation set, which I haven't included in this workshop. Okay, let's visualize the data. So right-click on that one and plot. So mean of data. So second overtone, I believe, water spectra. You can see first overtone of water spectra from 1300 to 1600. In this case, we have just the counters for those wave numbers or wavelengths. We can color code the spectra by, let's say, solute. So you can see we've got water, we have acetate, lactate, sodium chloride, and potassium chloride. You can see some spectral shifts there because of the temperatures. An important feature of this data set is that you've got a lot of replicates. Same samples are replicated under different conditions, different days, different temperatures. And we want to use those replicates to basically remove the interferences. I think historically you subtract to get rid of those, but I want to show you a different approach. So principal component analysis, let's do a PCA. So we drag and drop the data set onto the PCA. Somebody watches the battery here. Should be 1 hour. Hopefully it will be okay. Okay, some pre-processing. So mean centering is normally important. So let's do a mean centering here. Okay. Do we have a mouse pad? Or a piece of paper? Just A4 size. Yes, please, thank you. Just to have a, yep. Okay, mean centered spectra. Let's do a principal component analysis. And let's look at the score plots. Let's put a label. Okay. Let's make it. So you can see potassium chloride is creating a completely separate cluster here. This is a little bit strange because I think it has something to do with the experimental design, that this is clustered separate than the rest of the data set. But anyway, we include them. If you look at the water, pure water, PW, you can see you got pure water here, you got pure water here, you got here. So you got 3 clusters of pure waters as well. So it could be a day-related feature. So like I said, we have another label here called rep. So that the spectra that are similar or identical, but they have different perturbation, different temperature, different days, they're colored the same. You see all the blue ones are the same samples, but under different conditions. If you look carefully, you see that they are following a certain directions. You see that direction here. So if you can identify that direction, and if you can subtract it by way of orthogonalization methods, you could clean up that picture. I want to show you how you can apply that method. So let's close this one. So let's add an orthogonalization method that is called EPO. So external parameter orthogonalization. I'll have more detail on the theory side of things tomorrow. I just want to show you how it can be implemented. And then we say, what do you want to orthogonalize? We say the perturbation information. So we decide X block replicates. We say focus on the replicates. Whatever direction that those replicates are following, we want to identify and subtract those from the main data set. How many principal components we want to subtract from the perturbation? So let's start with 1, and then we can add to it. Because if you remove too much information, you run the risk of removing useful information. So you have to optimize that. So first, let's visualize what happened to the data. Plot pre-processed data. We look at all the data. And let's color code it. So you can see already even the shift in the temperature is gone. So the spectra are aligned. So the direction in which the temperature shift is working, which is kind of orthogonal to the rest of the information, is subtracted. Let's add 2. If you have two screens, this could be, because information is coming out. Temperature shift is gone, but you see the difference between solutes are even more clear. And you can even see that there's a concentration gradient appearing from that's hidden in the spectra. Let's do a PCA on that one. So it recalculates everything in the background. So you already see that the first principal component versus the second one here. You can see there are two main directions is being identified here. If you want to see that. And if you look at the replicates, you see identical samples are more overlapped now. So they're all tightly grouped together. Then you can look at second versus third principal component. Let's use a different method, which is the topic of tomorrow's discussion. It's called Generalized least square weighting. So it's very similar to EPO, except that you can fine-tune it much more tighter. So you can gradually increase or decrease certain dimensions. So shrink or emphasize or expand certain directions. And again, we say we work with rep. And let's add some weight to this. Increase it to 0.5. So look what you see now. It's much more clear. And do a PCA on that. Color coded. So you see that potassium and sodium are kind of getting close together. So that is what is expected. Sodium and potassium are not really very easily distinguishable if you look at the water spectrum. And this is clearly showing that. But you see all the waters are now centered close to the middle. So there's a concentration gradient also. And you can see you have two principal components that are orthogonal to each other, 1 and 2. Two different directions that are orthogonal to each other, that are emphasized in this picture. SNV. SNV is quite important to correct for the scatter correction. EPO cannot, or GLS weighting cannot correct for that multiplicative effect. So you need to add a scatter correction method. EMSC, on the other hand, can do that if you can apply a scatter correction filter on top. That could do similar sort of effect. So let's add an SNV to this. Pre-processing. SNV. Yeah.
Just the MATLAB script that you provided, this is the data, or I'm confused about what is in the MATLAB script, the data?
There's no MATLAB script. There's a data set and there's this program.
Okay, that's right. So
Yeah. But if you want to do, because you see there's tedious clicking and opening this window and zooming, you can automate all those by MATLAB.
But in Solo, in the Solo program?
In the PLS Toolbox version, which is the MATLAB version of this. If you see, I have the MATLAB in the background.
Yeah.
So you can program all of this. Because for the competition data, I had to try all sorts of different optimizations to make sure that you get the best result.
The MATLAB script there, what you sent this?
This is a GUI. What you're seeing is a graphical user interface, where you can close everything and just run the codes, and you get the displays you want. Yeah. And tomorrow we'll have a feel for that. But I just want to quickly show you what you can do and how important this can be for your work in aquaphotomics. So we want to add S and V to this to correct for that multiplicative effect. S and V, we add it to the list. So we have got an S and V step followed by GLS weighting, followed by a mean center. Let's do a PCA on that. No, I think it's clearer now. So that SMV was helpful to. So you got 3 distinct directions. I can even make it 3D. So if we add a third principal component as a third dimension, you can see that lactate, which is organic, is extending into a third direction. So let's rotate it. Oh, I think we don't have the third. Okay. It's 1, 2, and 3. I want to. Is clearly 3 orthogonal directions. Lactate, 2 salts that are very similar to each other, and the third one acetate, and water bang in the middle. So now I want to overlap the concentration gradient. So if you go color by, you can load your concentration data on top of that. You say, we load from the CRY block and molar concentration. So you can see from low to high, you can add a gradient bar there. 0 concentration to 100 millimolar. Each salt clearly showing that pattern there. On the raw data, there's no spectral subtraction. So we are just subtracting the orthogonal dimensions of the interference from the useful data.
And now you can take the loadings.
You can?
The loadings, can you show the loadings?
Oh, loadings, yes. This is more meaningful for you. I was trying to avoid that. But anyway, loadings are here.
Why do you try to avoid it?
Because I don't know how to interpret them.
Yeah.
But you know better. So you can have the loading 1, loading 2, loading 3, and then you can put the. I think that is good for interpretation now. Interference is gone. Now you can see the real signal. And you could probably focus on understanding what each one is. How much time do we have? Now we could test the test set. See how it works, this model, on the data you haven't seen before. Let's close this. So we load test spectra. And we say predict. Just close this one. So predict based on PCA. So it projects the new data into the old space after applying the same pre-processing that was applied on the calibration set.
This is very important. So you do the same
Yes.
orthogonality.
Yeah, but based on calibration set. So it knows nothing about the new set. It applies the same orthogonalization that was modeled in the calibration step. So it's, yes, that. So that is what you can use then to predict the competition data. But you can do other type of analysis. For example, you can do other classification methods like PLSDA or SVM. I got the best result from KNN, and I will present that tomorrow. And for regression, local regression was the best for me. So let's see the PCA on the test set. Let's close. So here, what you see is just the test set. When you double click, it should open that block. So you can see there are fewer data points because test set is smaller. But again, the same 3 direction. But then you can overlap the calibration data. And then you can color it according to test calibration. So you have got calibration and set, and you can see clearly there. So it's a no-brainer that you can identify some of those samples. The problem is when you get closer to 0, and that is the trick, how you can identify there. And my answer is you can't below limit of detection, but because your experimental design is not flawless, I took advantage of those, and I know exactly what day you did what. I use that information to predict things that are below detection limit. The second prize winner also used a similar method. He used a rep file method, which is an orthogonalization method. So first prize winner and second prize winner used the same method. So I think something worth exploring, this sort of methods. And if you apply a KNN model on these ones, when you get close to 0, also you can do a very successful identification. But what I did, I used the full spectral range. I didn't use principal component analysis because I think there are additional dimensions that are important for identification of samples. So it's a simplification of more complicated tasks, but hopefully it gives you some idea what can be done with this data. There's a lot more you can do. You can use these functions that the software provides to you and use your own functions and combine the two in the MATLAB version. So if you have any other methods you want to apply, you can add it to these capabilities. Since most of you don't have this software, it's no more interactive. That's why I just went through this fastly. I don't think I have much more to say unless you have a particular questions or you want to see anything in particular. But much more on theory. I have a talk tomorrow morning in chemometric session. So you can find the outliers by looking at some hoteling versus residual plots. You can
Find the outliers.
sorry.
How do you find the outliers?
Yeah, they will stand out. Yeah, if you look at the residuals versus hoteling, normally outliers come here. Yeah. So there's a cleanup step always before doing any data analysis, and then out. So all this was done by mixing the potassium chloride data. You can remove that and the picture will be more interesting. Or you can just focus on the water spectra That's what was done in the that EMSC work. They just focus on the water spectra, the first principal component of the water spectra, and just subtracted that in EMSC. Yeah. To do that, you need to do principal component and save the loading, and load the, as an external clutter. So if you go to clutter here, if you go to detail, you have to use it here. Then you need to use it as an external clutter in EMSC. But you can have EMSC as well here. So if, yeah. I tried EMSC as well for the composition, but I got better result from GLSW.
So you generally would recommend always GLS?
It is
For this type?
fine-tunable, so you can change it slightly and you can see how it affects the result. With EPO or EMSC, you suddenly remove one dimension completely, and maybe the solution is somewhere in between.
I have a question regarding that threshold that you said. I don't understand what the number means when you.
That is tomorrow.
Okay.
Yeah, that's the theory. So that alpha is the gauge. So the lower the alpha, the higher the weighting, the more shrinkage of unwanted dimension happen. Tomorrow I'll have some slides to explain that better, hopefully.
Is it possible just to show what happens, for example?
Sure. So we got a GLS weighting of 0.0005. So let's reduce it further. Let's add. So what happens is too much deweighting. So you will see the result now. You see? So what happens is removing too much information. It's still a clear classification happening, but I believe that you're left with noise with certain part.
But then you can do the writing separately from different components, like different solvent, solutions.
Oh, yes. But what I decided to do was replicates, I use old replicates, no matter what they are, because they're the same thing. And I got the best result when I included all of them. I tried just water, just... So finding the dimensions that are disturbing everywhere. We want to remove those and keep the information that is there. But how to optimize, that is not easy. Finding the right thing. This is sodium and potassium. Now, do you want to decrease it? You see what happens if you decrease it. Point 1. So it should be less deweighting. It means you should get more of the spectra. So it's similar to that one principal component analysis case. There's clearing up, but not enough. Yeah.
So how generally are you doing the optimization? You're trying different levels?
Depends on the aim of the. So if the aim is to predict unknowns, so
just based on the.
Yeah, you want to have a maximum classification. So that is the aim. If it is if it's quantification, you're looking for the lowest error. But I think my aim is always to have a visual understanding of the data. And normally those are the winning solution, when the picture tells you you have something. Because you see where's the minima, where's the best solution. You know you're not there yet. You have to add to the weight there.
This is really useful. You don't need to, for example, use spectral water for correction. If you don't use, for example,
you use it, but in a different way. We are still using the spectra for water as well in this correction. But we clump it together with other salts. As long as they're the same sample, we say they are the same sample. So let me show you how the data is sorted. So I'm just opening the data set. So you can see there's a label there. And for the reps, so these are all the same samples. Yeah, so we color code them based on. All you need to know is that they are the same sample. You don't need to know anything else, as long as you can. So my theory is you can use your old studies or all of different groups. They have their own data set. Merge them together. As long as you know what samples are the same, different instrument effect, different temperature effect could be removed potentially. I think this meta-analysis could be very valuable. And you don't need to design a new set of experiments. You use your old data sets for better results, hopefully. So when you see these pictures, you believe in aquaphotomics. So there is information there because those patterns are telling the story.
And also, for example, you could say you have 5 consecutives, I think in this data, of each of the samples.
Yes.
And we want this consecutive spectra bring information about the sample itself. So if we want to use these 5 consecutives as an information for the sample, what should we do?
So that's what we give them the same color. And as I will explain tomorrow, each group of these samples will be mean-centered according to that group. So we do a cluster centering. Rather than mean-centering on the whole data, we do it on those groups. So we said the difference between mean of different groups is not something we want to get rid of. That is the information. The difference between the samples after correcting for the mean of each group, after class centering, that is the perturbation. That is what we want to get rid of. So after mean centering each group, we cluster them together. And then say, now do principal component on this one and remove those factors because those are perturbation. And I have some slides tomorrow that hopefully will show that clearly. It's a very useful software to work with. Any other questions?
So it already becomes a discussion time. So if you have some question or comment from the floor. A question?
You mentioned this is
Microphone?
so it's okay. So you mentioned that it's PLS toolbox. Is that the eigenvector research?
That's right.
Toolbox? Okay. So a lot of this is based on that. How much is upgraded from that, and how much is roughly the eigenvector research, and how much is added to that?
Added by who? What do you mean added
So
to?
you have PLS toolbox, then you built upon that. So you said you used PLS toolbox. for
Yes.
this icon, and then how much is added to, what are the features that
It
are
depends what you want to do. For example, I needed to do TSNI for visualization. So I used other MATLAB functions to do that on top of that.
Yeah.
Because I found out that PCA is not sufficient to give you a whole picture. PCA emphasizes distance samples. So you lose information about localities of what's happening. Especially that middle bit of the clusters, when the water get close to water concentration, you don't see what is the dimensionality of the data. With other methods, which machine learning people are using all the time, TSNI, for example, you can see the local neighborhoods.
What
Uh,
is PS?
That's a visualization method.
Was it
I'll- Again, tomorrow I will show you a slide on that. TSNI, so it's a T-distributed stochastic neighborhood embedding. But there is a method that shows you what is the closest neighbor in a very busy neighborhood. With PCA, you can't see that. It will be passed on to 10th dimension. You never look at that.
Any other question, comment?
Yeah.
All right, thanks again. So now we'll have the coffee break from 5 o'clock.